Hello and welcome to this YouTube channel. My name is Lucas and I'm joining you today to talk about convolutional neural networks. It's an quite old but my neural network architecture often used for image classification, but the big deal here today is that we'll be creating this architecture from the scratch, or almost from the scratch at least, as we'll be using PyTorch as the base model of our model, but mostly to make use of all the device features necessary in this process, as I will be training this model locally on my Mac, making all use of MPS. I'm super excited to talk about this topic. I hope you to enjoy it with me and you follow me from the point of view of my VR. So no more talking and let's get started. Right, so let's get started by create a new Python environment. I'll be using Conda for this project here, as it's super simple to create a new Conda project under these Jupyter notebooks on VS Code. I will need to select kernel here, Python environments, create a new Python environment, then select Conda, and I'll be using Python 3.11 for this project. It will install it super quickly, and my new environment will be under my workspace right here in this Conda folder. So right now I can get started by installing my libraries. I'll be using Open Datasets to download the Kaggle dataset, also NumPy, Matplotlib, TiltKDM, Torch, and Torch Vision. So let's run this code and install all these libraries. But first we need to install ipykernel. This is a requirement for the Jupyter notebooks. It installs super quickly, so this is not a problem at all. And once it gets done, it will start back to these libraries here. Alright, so they are all installed now. Let me only clear these outputs here to save some space. And then we can import all the libraries we'll be using for this project. And the first thing, we only need to double check if Torch is able to identify my MPS device, my Metal GPU actually, because old versions of Torch might not be able to work with MPS itself, and then this is very important to double check it before starting your training process. So let's run this code, and here we can actually see that we have Torch using MPS instead of the CPU itself. So now we can actually download this dataset from Kaggle. I'll be using here a super simple dataset from Kaggle. This is only satellite image, but this dataset is almost ready to train. We only need to apply a few steps, a few transformations in this dataset on each image of this dataset before using them to feed the model. So let's download this dataset. Let me run this code. And the first thing here is that it requires me to pass my user credentials. So you can get these credentials from your user settings, and under API you need to create a new token. You only need to confirm that option and it will download a new file to you. You only need to open this file, copy your username, paste it in this window here, and also the token. So far so good. It will start downloading my dataset directly from Kaggle using Open Datasets. And while it actually gets complete, let's discuss the data arrangement here locally in my machine. So I will have the root folder. The root folder is this root folder here where my dataset is being downloaded, but I also have my main dataset folder. And this is actually the arrangement of class and image. I will show you exactly how it works when it gets complete here, but we also need to split this data into two separate samples for training and testing this data. But it's super easy. I will show you how to do all these steps. You will create a new directory for the training image and also for the test image. It's quite simple and it's not something very troublesome. There are actually many ways of showing this stuff. I will show you one of them. It's not like a rule of thumb to work this way, but the way that I have implemented it here is super simple. Then once complete, it's almost done. Okay, it's complete now. I can show you the arrangement of the data here onto the main folder, the main dataset folder, the Euroset folder. And as I said, we have a bunch of images here, but they are arranged on subfolders of my main folder. And each of this folder here is actually a class of image, right? This is the label for that image itself. For each image that I have here in this collection, I also need to have the classification of that image, because the real goal here is to classify the image. So before feeding my model, I need to have this information to use in my loss validation. So far so good. The first thing that we need here now is a list of classes, because we need this identification while working, actually while training the model. So I will, as I said, I will use these folder names here as the label, because they are my class names. And then I only need to list them, but first I need to run this code. Then I have this list of folders here, but it also includes some files that I don't want to have them include, because they are not actually classes, right? And I also need to sort these subfolders here to sort my class names. I will run this script here only to sort and remove these unnecessary files from my final class list. And then here I only delete the train and test directories, because if I run this script again and I already have the train and test directories created before, I will actually remove them first. I don't have any of those actually directories created here, so it's empty. And then I can create these directories right now. And then we have the test and train directories. And as I said, it's super important to have this class identification. Then we need to create this mapping, because the output of the model itself will be a number. And then we need to find a way to create this link between the class name and its number representation. So here I have this index map, right? So each of this number is actually a representation, a numerical representation of a class name. Then let's run the class map. So then we have the class map available. And now we can split the data set itself. I'm using 8% of these image samples for training and 20% of them for testing. It's important to have this bigger number for training, because as I will show you, when we feed the model, we pass not only one image at a time, but a bunch of them. So let's run this script. And then we have the new directories of training and test data available here. But now we have a different structure, because the class names, the labels of the image here are now numbers. And as I said, because we need to create this numbering representation of the class name. So far so good. we can go to the pre-processing step of our work. And the first thing is that we need to apply some transformation on each image of the collection. And here, the first one, we need to convert that image to the tensor format, to a matrix format. And after that, we need to normalize the image by giving it a mean and also a standard deviation in the color channels of my image. I'm going to show you an image sample here very quickly so then we can understand it a little bit better. As we can see, all these images here, they have the same resolution and the same color channels. This is RGB image and they don't have an alpha channel. So we only have 3 color channels for this image. And this is why we only pass these 3 arguments here in the mean and in the standard deviation. So let's run and create the transform. And then we can create the dataset and the data loader for training. The way that we create this dataset is by scanning the root folder of my training data here. And it will collect all the images from this subfolder, but also the classes. So it will actually result in a list, actually in a tuple of lists of images and labels. I will show you next up, and then we need to pass the transform argument here, because for each of the images found here in this folder, we will transform them to get them ready to be used. So then we can create a data loader, and the data loader uses the data set itself. But in the training loop, we don't use the data set. We use the data loader because we need to feed the model with a batch of images at a time. And here I'm using 64 images as the batch size. And I also need to shuffle these images. And I'm using 2 threads to do this work. I need to do the same thing for the testing dataset, but the only difference here is that I'm not using a batch size of 64, but only 1, because I only need 1 image at a time to validate my model. So far, so good. We have the datasets and the data loads ready here. I only need to run this code. Okay, and then we can display 8 images here only to get a better understanding of this process. I will define this image, and here I will get the next iteration of the train data loader. I will run this code here and show you that now we have a tuple as the result of this iteration, because we have image and its labels. So for each image in that index, we will have a label as well. So as said, we have 64 images on each iteration of the data loader, as you can see here, but also 64 labels. Okay, then we can show these 8 image samples in a grid and also its labels. So if we have a look here, the label itself is a number, that number 7. So number 7 is actually the numbering representation of this class name, residential for this case. And if you see the image itself, it might be actually equivalent to this label, this class. So this first one must be a residential area. So far so good. We can finally create the model architecture. And to get started to this model architecture, we first need to understand that we are inheriting from nn.Module here from PyTorch, because we'll be using some features of PyTorch itself, as I said in the beginning of this video, like the device features from PyTorch, and also the implementation of all these layers. I will be using the standard definition of PyTorch, but we will define all these layers by ourselves, right? And I will try to explain it with minimal details, but in a way that you can understand it easily. And then this is a definition. This is my architecture. We will work with 3 convolutional neural networks, 2 dropouts, and 4 fully connected neural networks. And I'm using the conv2d from PyTorch to create the convolutional neural networks. This first argument here is my color channel number. As I said, we only actually have 3 color channels on each image because it is RGB image, right? And it is a 64 by 64 resolution, and we are using only 3 features. Actually, we will use only 3 features of these image and a stride by 1. I will explain it a little bit better, but the point is that the result of one of these layers will actually be used as the input of the next one. So the same thing happens here. And then I only have different inputs, like for actually different arguments for inputs and outputs, because we need to consider the previous one output and the next one actually output. So far so good. Then we have the dropout. The dropout, we will be using dropout as a regularization technique, sorry. And then we will have 2 dropouts, and also the fully connected neural networks. This one works like a MLP classifier, and they will actually go in the very ending of our layers of the architecture itself. So then we have the forward method. The forward method is the method where we receive an input. This will be an image in the tensor format, and then we'll get this image and pass it through all the layers that we have defined here. So the first one is the conv1, that convolutional neural network. Then here we'll actually extract many features from this image, and the output of this convolutional neural network will be used to feed the next one. So it will be the input of the next layer. But in this case, we have an activation function here, the ReLU activation function, only to introduce non-linearity and solve actually a problem with vanishing gradients. So before providing actually the input of the next layer, we need to pass it through this activation function, and the result of the activation function will feed the next layer, the conv2, and this happens till we actually get to the max pool layer here. It will actually work as a filter. It will extract, it will reduce the spatial dimension and extract only the maximum value within each window or region from the output of this last ReLU function here. And then we will pass the result of the max pool to the dropout, because we want to discharge some values here to prevent overfitting. So the result of the max pool is actually the input of the dropout. And then we need to flatten this result from the dropout, because then we need to reshape the tensor to feed the next fully connected network. So once we have a new reshaped tensor, we can pass it to the fully connected neural network, and it also uses a ReLU as an activation function, and then it feeds the dropout. So then we can reduce actually the dependencies between neurons. And then the result of this dropout here will be used to feed the next fully connected network, right? And it will happen until we reach to the softmax function. And this will actually calculate the probability for every possible class that we have in our data set. And this is very important to understand the problem before creating your architecture, because it's super clear here that we have a multi-class problem, and this have direct impact in how we define this algorithm here, because many of these functions, they will work better in different situations. Like for a softmax here, for example, we as this is a multi-class problem, a softmax fits super great here, I would say. But also the ReLU itself, and this is very important to understand before creating your architecture. But many times you only actually base upon some white papers, and then you can get this definition directly from your white paper, and you only need to reproduce it here. But many times you also want to modify this architecture by yourself, and then you can try something different, get different combinations of different techniques and combine them, trying to create something actually maybe better than the standard one. So far so good. Let's only run this code here, and then we can create the model. And this is an instance of this class that we have just defined. Then we can print this model only to check for the structure of our model. And here a very important point is that we need to convert it to the device. What is the device here? The device here is the MPS device that we are working on from Mac. So we actually need to convert it because we need to load all the tensors to the GPU instead of the to the GPU memory actually, instead of the regular memory. So at this point we need to actually ask the model to download all tensors to GPU directly. So let's run this code, but the architecture remains the same. It only actually loads the tensors to a different memory. Then we can create the criterion. The criterion is actually the loss calculation. I'll be using a cross entropy loss calculation here, and also we need the optimizer because we need to understand if the model itself is learning something or not, right, during the training step, the training loop. So this is how we calculate if the model itself is learning something or not, and this is actually how we adjust the model itself, trying to make it actually learning better, I would say. So let's create a criterion and also the optimizer, and then we can define the number of epochs used for this training loop. This is the number of times we will run over the data set and feed the model during the training process. So next up, we can create the test iterator, because during the training process, once we feed the model, we need to calculate the result of this model by using this test made samples. Let me run this code as well. And finally, we can run the for loop, the training loop of our model. And here we have, as the first thing, a for based upon the number of epochs, so it will run 30 times, right? But it also has a sub loop here that will actually be using the data loader of the training of that training folder. So for each iteration here, we'll have 64 image samples and also a tuple of images and labels, not only images. So for each data that we have here, this is actually a tuple of inputs, which are images, and also labels, which are the classes of images. And at this point, we also need to convert this data to device, actually to load this data to the GPU tensors instead of the regular memory. So after that, we can start by cleaning the optimizer by actually telling the optimizer to be ready for the training, and then we can feed the model with the inputs, which are the images. So we are feeding the model with 64 image samples at once. And after the model pass all that image, all the 64 images through the forward method that we have defined here, it will output all the probabilities of classes by using the softmax itself. So then we need to calculate the loss for these outputs, and we are using the criterion. And the way the criterion will actually calculate the loss is by having the outputs and the real labels of that data. So then we can calculate how good this model is actually learning. So after that, we can backpropagate the loss calculated in this criterion. So then the optimizer can make adjustments in in the neural network weights. So then we can try to make it a little bit better in the next step. So far so good. Let's run this loop here and watch it training. It will take some time, so I will forward this video a little bit. It took over 30 minutes to finish training this model, but it ended up with a very good loss, only 0.02, which is very good. And now we can evaluate this model. I will put this to run because it will take some time. And what we are doing here actually is setting the model to the eval state. So it will disable some layers that are not necessary for inference. And we also use the no-grad from Torch because then we can disable gradient calculation. It will reduce memory and also GPU usage. And we create actually an iterator here. So we run over a few samples of maze and from the test data loader, and then we feed the model and get the prediction of the model. So then we can evaluate the final accuracy of the model. Let's check the accuracy, and it's 0.84% of accuracy. It's quite good, but you can try to adjust some hyperparameters or maybe the architecture itself. Let's run one sample here so then we can check an image and its label. So I'm grabbing an image sample from the test data loader, and I will feed the model with this image and finally print it with its label, the predicted label, the predicted class of this image from the model. And this one was classified as an herbaceous vegetation. We can run it over and expect a different one as it grabs images here randomly. Yeah, and this one is a permanent crop. So this is the final result of our training process on MPS. Looks quite well. You can also try it on CUDA itself. You only need a few adjustments. You can try it on Google Colab. It's fine. But the point here was to run and train this model locally on a Mac. So hope you to have enjoyed this, and see you next video.